students working within each of these. And just so you're aware, previous talks have been recorded and are being uploaded to the MSA YouTube channel. I think currently we have weeks 1 and 2 uploaded, so go check those out. Week 3 will be uploaded soon, I think. So without further ado, we'll welcome our 2 speakers today. The first speaker is Vince Rienzi. He's a second-year student in the Nakamura group, falling under the electronic and photonic materials discipline. His email is given here if you want to reach out to him. And a quick fun fact is that he played Frisbee for 5 years at Lehigh while getting his bachelor's and master's, and was one of the head captains in his 5th year. And then following Vince will be our second speaker, Lily Hallett, second year as well, in the Harder group under the functional and quantum materials discipline. Her email is also given if you want to reach out to her. And Lily's quick fun fact is that she started a business making and selling rock climbing holds in Quebec, Canada, which is pretty cool. So without further ado, Vince, would you like to take it away?
Yep. How does this look? Sweet. All right. Thank you, Ashley, for that introduction. Hi, everyone. My name's Vince. I'm in the Nakamura group, and I'm a PhD student at UCSB Materials. And today I'll be talking about efficient LEDs and lasers using nitride semiconductors. So to start, I'm going to start kind of talking about my journey through UCSB, and then towards the end, talk about my actual research. And so to start, why did I choose materials? Well, I'm from a pretty small town in South Jersey. I was always good at math and science. However, finding a major that sort of fit my interests was difficult. Like the conventional engineering, such as chemical engineers, mechanical engineers, didn't really interest me, but I knew I wanted to do something math and science related. And so I expressed these concerns to my high school chemistry and physics teachers, Ms. Dare and Mr. McCulley. I'm actually wearing a Genius shirt that was supplied to me by Ms. Dare. So, you know, very important people in my life. And I expressed these concerns to them. And Mr. McCulley mentioned that one of his former students, Neil, was going to be giving a talk about materials and that he thought I should listen. And so Neil was getting his master's from Rutgers at the time, and he gave his presentation about what material science was, and I was hooked. I knew this was the major for me. And so it wasn't until after I got accepted to UCSB that I kind of heard through the grapevine that Neil was actually at UCSB. And so it was nice to catch up to him during visit weekend and kind of have that full circle moment. That was really fun. And so for undergrad, I ended up choosing Lehigh because it was only 2 hours from home, and so my family could kind of visit, but it would be a little bit of an inconvenience, sort of. So it was like the perfect distance, I thought. They also had a rich materials history because Bethlehem Steel was a major company nearby. So there was a lot of metallurgy and just material science knowledge in general in the area. And I also helped with the microscopy school for a few summers and going into my master's. And actually the summer after my master's, I was able to operate a TEM for one of the courses and help out there. So that was pretty fun. And as Ashley alluded to, I played Frisbee for 5 years. And even though this is a low quality image, these are all very high quality people. And I would be doing them a disservice if I didn't mention how important they were to me for my time at Lehigh. And so the undergraduate research that I had at Lehigh was approximately zero. I'm probably one of the few PhD students in the UCSB materials department who was not part of a research group in undergrad during the school year. My only research experience was the summer going into my junior year. And just because you didn't do research in undergrad does not mean that you will not be a great researcher as a PhD student. So I worked with Professor Nick, who oddly enough was also a UCSB alumni. And what he did was he did thin film growth, where basically you add a certain molecule to a chamber, you let things equilibrate, you remove that molecule, you then add another molecule, molecule B, wait for things to equilibrate, and wait for this molecule to bond to molecule A. You then remove that molecule, you repeat, and then you add molecule A, and you kind of build up this structure. And so that was kind of the overall theme of his group. And what I did specifically was more surface characterization, kind of looking at how stress had played a role in the deposition of these films. I would be lying to you if I said I understood or had an appreciation for the motivation for what I was doing, or even what was going on in the group meetings. So if you're confused at the start, it's fine, it's normal, especially when you're joining a new group. But it was nice to still be able to contribute to the bigger picture and help out. So the research experience I had was nice, but I wanted to kind of get a full picture of what I wanted to do with my life. And so the next logical step was to try to get an industry job, or an internship. And so the summer before my senior year, I interned at Lockheed Martin, and it didn't take long for me to realize I did not want to contribute to the war machine that is the United States military, where at Lockheed, basically the site I was at, what they did was convert regular news helicopters into attack helicopters, which is cool to see that fly in, but it's not really what I wanted to do the rest of my life. And so there are much bigger issues in the world, I thought, than starting wars, and such as climate change. And this is kind of when sustainability really started to matter to me. And so I had to do some thinking about what could I do to really make an impact in the world, a positive impact, something that I thought would be an objectively positive experience. And so that was when I kind of decided grad school was for me. I ended up staying a 5th year at Lehigh to get my master's. The only reason I was able to do that was because it was free. And so I had to find a project that interested me. Otherwise, I wouldn't really be able to sort of justify it. And enter Siddha, who is the 3rd UCSB alumni I've met along the way. Siddha was awesome. He's a great guy. I knew from my master's I wanted a pretty hands-on advisor who was kind of young, who would be able to guide me through this process. And specifically what his research was on was a monothermal crystal growth, which is pretty much high temperature, high pressure synthesis for stubborn crystals, stubborn materials. And so since he was so young, he didn't really have a lab yet. So I tried to help him build his lab, which through a series of unfortunate events is still getting built. And so because of that, I didn't really have a thesis or any research to go off of. So I transferred to a master's in engineering. But on the bright side, I got to play another year of Frisbee, which was pretty fun. And so I credit Siddha with a lot of my critical thinking skills, because it's my first experience to like trying to think through problems, and he was instrumental in helping me with that. So after my master's, I wanted to go further my education, get a PhD. I ended up choosing UCSB because Siddha was my first exposure really to electronic and photonic materials, and they were the most interesting to me. UCSB is pretty well known to be one of the top materials programs in the world. I didn't really have any funding secured through like NSF fellowships or NDSEG or anything like that, but I knew UCSB had plenty of money so that I wouldn't really have to worry about those horror stories you hear at other universities where sometimes, you know, funding just stops for whatever reason. It's also right on the beach, so I knew that was going to be a huge plus for me. And as you can see, this is Siddha during his time at UCSB. And so I also knew I wanted a hands-off advisor, at least during the first few years while I'm trying to get oriented. And that ended up being Shuji, who is pictured here. And so SLEEK is sort of the center that all of my research is conducted in, which is the Solid State Light and Energy Electronics Center. Shuji is my direct advisor, and he's pretty well known in the field because he pretty much invented the blue LED, which is kind of in every white LED that you see around you today, and it revolutionized how we live our daily lives. And so the other professors of note in SLEEK are Steve Denbars, who's professional, or the expert, I should say, in crystal growth. Umesh, who is more on the electronic side of things, and Jim Speck, who is more on the fundamental materials side. And so this talk is titled Using Nitride Semiconductors. And so when I say nitride, basically what that means is at least one group 3 atom bonded with nitrogen. So when I say GAN, that means gallium nitride. If I say InGAN, that's indium gallium nitride. And so GAN is really nice because it has a lot of applications that you can use it for. So one being UV disinfection. So quick PSA, public service announcement, do not try to drink UV light or whatever it was Donald Trump said. Instead, view it as like killing it before it enters your body. You'll be thankful in the long run. You can also use nitrides and semiconductors for next generation displays, such as flexible displays or near eye displays, and then many, many more applications that I don't really have time to go into now. So we should start this by kind of saying we have this full center dedicated to light at UCSB. But what is light? So light can be pretty high energy gamma rays from like supernova, collapsing stars, or it can be very low for radio waves or communication purposes. But for the purposes of this talk, we'll focus mostly on visible light. And so you can kind of see Roy G. Biv backwards a little bit. And then here you kind of go into ultraviolet light, and over here is more infrared light. Both of these are invisible to us, and the main reason we see these lights and why it's considered visible is just because of the sun that we orbit in our solar system just emits visible light more intensely than the other forms of light. And so a quick history lesson for on-demand light. We started with fires and candles, which fire, I think, might be the most important discovery of all time, right there with the wheel and opposable thumbs. But it gives off most of its light in the form of infrared heat that we can't really see or use. There's also, so the next generation was incandescent, which are step up, you heat up a metal to a really high temperature, but still not as good as we would like. And then enter LEDs, which are just objectively better. They're more efficient, they have a longer lifespan, and you can kind of tune the color to go pretty much anywhere in the Roy G. Biv spectrum and beyond. And so we know light's important, but how are we going to get this light? And so we do that through materials called semiconductors. And to kind of set the stage, electrons have discrete energy levels. And so these electrons are present here with discrete energy levels. And for metal, there's kind of a continuous distribution where electrons can go from a low energy state where they're kind of packed real tightly and aren't really able to move freely to a higher energy state with little to no energy change. And so this is nice because it lets them move freely. Non-metals, which are what semiconductors are considered, have this sort of forbidden gap where you need to add at least some sort of minimum energy to allow for electrons to be able to move freely. And so this gap corresponds to the type of light that you produce, where if you have a lower energy gap, an electron falling down will release sort of a low energy photon, such as red or infrared, just through energy conservation. Whereas if you have a higher energy gap, you'll be emitting blue, violet, purple, UV light, just because it's a larger distance that the electron needs to travel in terms of energy. And so we know semiconductors can be used for producing light, such as for LED devices. So why nitride specifically? The main reason is they're able to span from the UV to the infrared, whereas conventional phosphides, arsenides are only able to go from green to infrared. And so because of this, the sort of possible applications that you can think of are significantly more numerous, where you can span the full visible range. So that is something that no other material system is able to do yet. It's also a much younger material system in that there's other nitrides not even pictured here that are still in more of the theoretical developmental stages that have even more interesting properties. And so there's a lot of work that needs to be done and a lot of potential for improvement. And so I'll be focusing for the rest of this talk mostly on LEDs, but just to give you a little bit of an exposure of what a laser is. Basically, they only emit at one specific wavelength. So they have a very narrow spectrum. So if you go to half the maximum intensity, it's much more narrow than what an LED would be. The emission profile of an LED is spherical, hemispherical, whereas a laser is more directional in the way that it emits light. And then so for LEDs, they're more kind of general applications where it's just display, where you just kind of want lighting in a room or from a TV or something. Whereas a laser has more interesting applications, I would say, such as, telecommunications or atomic clocks and things of that nature. And so starting to kind of get into the nitty-gritty details of research. So to get to a longer wavelength, you remember that plot where we could span the entire UV to infrared with nitrides. The infrared portion was indium nitride, and the sort of intermediate stage was GaN. And so you can have, there's no bulk in GaN crystals, and so to form a red nitride-based LED, you have to have some indium gallium nitride grown on top of GaN. However, there's a 11% lattice mismatch between indium nitride and gallium nitride, and so this mismatch leads to poor crystal quality, which leads to defects, and then just poor device efficiency in general. And so as a result, nitrides are pretty efficient when they're blue because you need less indium. However, as you add more indium, this issue kind of gets exaggerated or exacerbated. And so efficiency drops off. And then phosphides, which only are able to emit green light, or the band gap corresponds to green. So to make an LED, it can only emit red light. And I won't really get into that, but basically the efficiency drops off when you get to green for all material systems. And so there's this thing called the green gap that research is trying to address. And so my research is on microcavity LEDs. And to sort of set the stage on that, first I'll talk about what a conventional LED is. And it's, around 5 microns thick. The emission is kind of sporadic. The intensity is all over the place. The wavelength isn't really uniform. But if you use a microcavity, it's more directional, more uniform, same wavelength. And so the microcavity is basically you have a standing wave where you kind of have 2 fixed ends. And so because of this, you're able to emit light. You're able to extract your light better because at this GaN air interface, where GaN is your LED, when you're at a maximum, when you're at an antinode, you're able to extract light more effectively than if you're anywhere else. And so that's easier to do with a microcavity because you're designing specifically for this purpose. Whereas with a conventional LED, it's so much thicker, there's so much variation that it's much less likely to happen. And so what we can do is we can sort of decide where the electrons get converted to photons in our device such that we're able to sort of achieve this profile, this wavelength profile that we want in our device. And so efficiency is a function of the number of photons exiting your device over the number of photons that are created in your device. This parameter is known as light extraction. And so what you can do is you can kind of plot for a given cavity length. So in our example, we'll call it like 200 nanometers or so, or 140 nanometers. You can have only 1 or 2 sort of positions where you can place your active region for this to work. And so just by fine-tuning your device thickness and where you're creating your light in your LED, you're able to increase your efficiency purely from just geometric considerations based on reflections and things along those lines. And so this helps us address the green gap, which is pretty useful. And so for my day-to-day lab work, first step is to grow a crystal. You can't really have an LED without a crystal. This buffer region is just to sort of improve your crystal quality. And so then you go from your crystal to sort of processing it and shaping it into an LED. Ignore these are kind of the nitty-gritty details, but basically you're just kind of trying to shape it into an LED, and you do that by sort of etching or depositing metals or insulators in certain ways, so that way you get a fully functioning LED. And you'll notice you have to be in a pretty clean environment for this to work. You can also characterize or test your devices. You can also perform simulations, so that way you know what is and isn't worth testing, and sort of see if your experiments line up with theory. There's a lot of data analysis, which basically is, why is this not working 99% of the time? And then something that was really nice for UCSB is that it's a collaborative facility where you're sharing facilities with other groups, other departments. And so the perks of grad school, there's a pretty flexible schedule. You get out of it what you put into it. You're surrounded by a lot of really smart people who can help you if you seek the help. Your problem solving skills will increase tenfold. It's really nice. And then you're on the leading edge of human knowledge. And so you can approximate all of human knowledge as a circle or a sphere. And then this is sort of all that you know after high school. After undergrad, you sort of get specialized in certain areas, take some gen ed courses, take your major courses. And so you kind of know a little bit. And then after your PhD, you're extending the bubble just a little bit. But it's really rewarding when you get to the leading edge of what we know and what we don't know. And so rounding out the presentation, just kind of my last pieces of advice. I encourage you to be curious. You're a student. It's literally your job to ask questions. If you don't know, ask. Some of your advisors have been working on this stuff since before you were born. I know Shuji invented the blue LED like before I was born. So it's not your job to know everything. Volunteering and community outreach. I'm a first generation student. My dad's a truck driver. My mom's worked 2 jobs for as long as I can remember. And Neil's talk literally changed my life. So I'm very thankful for him and always recommend trying to pay it forward. You're not alone. There's a lot of grad students who go through things, and there's specific groups and organizations here to help you out. So reach out. There will be someone willing to help. There's this cliche, research is hard. If it was easy, it would have been done already. Very true, but that's what makes it rewarding when it does work. You are more than just a grad student. You are a human being. If you have interests and hobbies, keep doing them. You're not just some cog in the wheel. Your opinion matters. And probably most importantly, be honest with yourself. If location matters to you, go for location. If you don't know if grad school is right for you, that's okay. Just as long as you're honest with yourself, you can do pretty much anything as long as you're honest with yourself. And so to end this talk, work hard, play harder. These are all things I've done while at grad school, not necessarily at UCSB, but during my time here at UCSB. A lot of climbing, a lot of bonfires, a lot of good times. So thank you. That's the end of my talk. And if anyone has any questions, I would love to hear.
Cool. Thanks so much for your talk, Vince. That was really interesting. If you have any questions, feel free to put it in the Q&A. But I have a few questions to start out. So you mentioned that when you were doing your master's, you were working with a relatively new professor, and now in your PhD, you're working with a very established professor. Mm-hmm. So like, what are the differences between kind of joining a newer lab and then joining a lab that is more established?
It's a good question. So At Lehigh, it was more of the undergraduate population was only 5,000, so it was definitely more hands-on, both in terms of lab work as well as conversations and meetings, and more personalized. Whereas at UCSB, a lot of the research here is funded by industry, and so it's more it's less personal and it's more independent, I would say. So a lot of self-motivation, which is why it's so important for you to be honest with yourself, because if the research isn't interesting to you, it's easy to kind of fall off the rails. And so I think that's one of the biggest differences, I would say, is the sort of hands-on versus the independence that I have now in my PhD.
Nice. So for you, what would you say was the hardest transition between going from undergrad and your master's to grad school?
Definitely when you first, I don't think Lehigh prepared me in terms of the academics. It was the coursework here was challenging for me, but not overbearing, because there's so many people you can reach out to and ask for help. So that was really nice. The TAs were super helpful. The cohort that I'm in is very inclusive, which I'm very thankful for. And then I guess lastly, kind of getting used to the research group as a whole, where they use a lot of jargon and vernacular that you're trying to get used to, that can be pretty overwhelming the first couple of weeks or even a few months when you join, to kind of get caught up to speed. So again, if you're new, ask questions. It'll make your life a lot easier.
Cool. And I guess one last question. You mentioned the green gap briefly, and this is not in my field of research. So I guess what's so important about being able to have an LED that emits green light?
So most of the pixels in your computer are RGB, so red, green, blue. And it would just cut down costs if you had to worry less about heat, because all the, well, not all, but a lot of the energy that doesn't come out as light comes out as heat. And so that will heat up your monitor. It'll just be more costly and more power consuming to be able to power your monitor. And so that's kind of the main reason, is because everything is red, green, blue to get the full color spectrum.
Awesome. Great talk, Vince. Very interesting.
Thank you.
Again, I love that diagram with the PhD needle sticking out of human knowledge.
Thank you.
So, yeah, so I guess virtual round of applause. And then we can switch over to our final speaker of this series. So Lily, you're going to take us home.
Okay, can everyone see my screen and hear me okay? All right, great. As was mentioned in the introduction, my name is Lily Hallett, and I'm a second-year graduate student in John Harder's group at the Materials Department here in Santa Barbara. And today I'm going to be talking about exploring quantum materials through computation. And let's see. Sorry, I'm having a little trouble advancing. There we go. All right, so I'm gonna begin talking a little bit about my personal journey to graduate school, and then I'm gonna give a broad overview of the field of quantum materials, followed by an example from my research on a material that I work with called strontium titanate. And I'll also discuss briefly the importance of computation in material science. So beginning with my personal journey, I actually did not graduate from high school, and I didn't return to school until I was 22. When I was a teenager, I was really only interested in rock climbing. I just wanted to work at the climbing gym, maybe be a personal trainer. And at 19, I moved to Quebec, Canada, after visiting there on a climbing trip. And I worked a series of manual labor jobs, construction, renovation, which I really enjoyed. And I also started a business making and selling rock climbing holds made from polyurethane. Here I am in my pouring mask, as polyurethane is pretty nasty to work with. And it was actually this experience that got me interested in material science, because I started to think about, how can we make more sustainable plastics? And unfortunately, about a month after this picture was taken, I hurt my shoulder really, really badly rock climbing, to the point where I could no longer do any of the work that I had been doing before. And it was really devastating to not be able to do the things that I loved anymore. But I took that opportunity to get my GED. I moved back to the States to be closer to my family. And that same fall, I enrolled in the chemical engineering department at the University of Arkansas. And I knew I was interested in research, and I had this interest in sustainable plastics. So in the spring of my freshman year, I reached out to Professor Stefan Kiljanek in the chemistry department, and his lab focused very broadly on chemical reactions, which produced starting materials for polymers from plant material, which aligned with my interests at the time. And there was an organic synthesis component to my project. And there was also an electrochemistry component. And I found that I was really much more excited about and engaged with the electrochemistry component of my project. And so in the summer after my sophomore year, I applied to the Amgen Scholars Program at the California Institute of Technology. And I was able to work with Professor Nathan Lewis in the Chemistry and Chemical Engineering Department. And his lab focused on solar fuels. And I personally worked on making and characterizing bimetallic catalysts for CO2 reduction and continuing my electrochemistry research. And as I continued in this, I realized that what I was really interested in was how electrons were behaving in different systems and in different materials. And I wanted to focus more on that. So the summer after my junior year, I applied to work at the Materials Research Lab at MIT with Professor Carl Berggren in the EECS department, Electrical Engineering and Computer Science. And I did more of a solid state physics project here, where I was sputtering molybdenum nitride thin films for nanowire single photon detectors. And this is the sputtering system that I used. And then this is the cryostat that I used to measure the superconducting properties of the films. And after this experience, it was very clear to me I was much more interested in solid state physics and in the physics of electrons in materials. And I was also really interested in quantum phenomena like superconductivity. And so I applied to a lot of grad schools, and I chose to come here to the University of California, Santa Barbara. And I wanted to work with John Harder in the materials department, and his lab focuses on quantum materials. So that's what I work on now. And I actually do purely computational research at this point. And my switch to computation was really actually motivated by the fact that the shoulder injury I got before I began undergrad was really kind of a long-lasting issue, and it was really painful for me to do experiments, and I realized that just wasn't possible anymore. And so I made the switch to computation, and I really ended up loving it a lot. So it turned out to be a positive end to the story. And so I just wanted to kind of summarize some tips I have for just succeeding in academia in general, or things that have worked for me. The first thing I would say is to be proactive, reach out to professors, apply for different research opportunities, apply for as many grants and fellowships as you can. Just really be active in seeking out the opportunities that will help you move forward. I would also say be flexible and keep an open mind. I ended up in a very different place than I started. I never thought I would go to grad school. I definitely didn't think that I'd be doing computation, but I'm very happy where I am. So just be open to the fact that your trajectory might change, and that can actually end up being a really good thing. I would also say really believe in your ability to improve. If something is really challenging, don't write yourself off as just not being good at it. View it as an opportunity to grow. And lastly, I would say it's extremely important to be able to communicate your strengths to other people. And this is maybe something I picked up in sales, but I think you could be the best person for the job, or your research could be really, truly incredible. But if you can't convince other people of that in writing, in presentations, in face-to-face meetings, then you're going to be really limited. So it's really important to be a good communicator and to highlight your strengths. So with that, I will transition to talking more about the science. So first, I'm just going to kind of broadly talk about what quantum materials are and give some examples of applications. So what are quantum materials? Essentially, they're materials that have properties that can't be described by classical physics. So we need quantum mechanics in order to describe what is going on in these materials. And a lot of the interesting properties that we find in quantum materials arise from the fact that electrons are interacting very strongly with one another. And that can lead to really interesting behavior. And I'll discuss a couple of examples in this talk, but there are many others. And so what are quantum materials used for, and why are they important? So the most obvious application of quantum materials is for quantum computing. And why we care about quantum computing is that it has the potential to solve extremely complex problems that can't be solved with classical computers. So this could include really complex optimization problems, like optimizing the usage of resources or land, which could help mitigate climate change, modeling really complicated things like weather patterns or systems in the human body, which could have applications in medicine. And quantum computers could also be used to model quantum systems, which could really help move computational research forward in physics and chemistry and material science. So quantum materials also have the ability to improve classical computers. And this is important because we use classical computers all the time, and this requires a lot of energy. So if we improve materials for classical computing, this has huge benefits for society. So just a couple examples of this. So giant magnetoresistance, which I won't really go into, but can be used for data storage. And this actually won the Nobel Prize in 2007. Graphene is a quantum material, and it can be used for flexible electronics. Another really interesting kind of subfield of quantum materials is quantum magnetism. And this includes spin liquids, which I won't go into too much detail about the physics of spin liquids, but I'll just say that they have applications in data storage and memory. And these materials occur in certain geometries. Electron spins interact with each other in interesting ways. And I encourage you to look into this on your own if you're interested. There are even applications for quantum materials in the energy sector. Solid state batteries with very high energy density were recently produced. This could be good for electric cars or other devices. And also, because we're studying such fundamental physics, there could be a lot of other applications that we really can't even imagine yet. But by understanding the behavior of these really interesting materials, this could lead to technologies that we really just can't even fathom at the moment. So it's a very exciting field. And before I get into some specific examples, I wanted to briefly describe, what quantum mechanics is, because I realize some of you may, have no background in quantum mechanics. So in classical mechanics, we use Newton's equations to give us the position and velocity of classical particles, right? So if I kick a soccer ball with a certain force, Newton's second law will tell me, where that soccer ball will end up at a given point in time. But these equations don't apply to extremely small objects like electrons, for instance. And so in quantum mechanics, and this is the most intimidating sentence that I'm going to say in this presentation, so I'll explain it afterwards. But in quantum mechanics, we use the Schrödinger equation to get the wave function of a particle. Now, I've written the Schrodinger equation here, but the details of this equation are outside the scope of this course. But the wave function that I mentioned is represented by this variable psi. And so what is the wave function? What information does this give us? So the wave function basically gives us the probability of finding a particle at a certain point in space and time, where in contrast to Newton's equations, which will tell us exactly where the particle is. And so quantum mechanics gives us statistical information about the probability of certain events occurring, which is very different from what we're used to in classical mechanics. And I also just wanted to briefly talk about the idea of quantization of energy. So when we solve the Schrodinger equation, we basically find that only certain energy states are allowed. So the particle can only occupy certain allowed energy states. And you could kind of think of this as an analogy to money, right? You can pay for something with a $1 bill or a $5 bill, but not a $4 bill. So there are only certain allowed energies. And as we add energy to the system, the particle will make discrete jumps from one allowed energy state to the other. And we call this quantization of energy because the energy occurs in discrete packets or quanta. And this is, of course, where the term quantum mechanics comes in. So the last kind of fundamental concept I want to talk about is that of superposition, because this actually relates to quantum computing. So I'll just explain this in a very, hopefully basic and accessible way, but imagine we have a system with two possible states, and we'll call these states up and down. And so, let's say we have a particle that can either exist in the up state or the down state, and we have it in a box somewhere, and we might wonder, I wonder what state the particle is in right now. Is it up or is it down? But what quantum mechanics tells us is that this question doesn't really make sense to ask for quantum particles, because what we know is that quantum particles can be in a superposition or a combination of two different states at the same time. And it's only when we observe the particle or measure the state that the particle, quote unquote, chooses one state or the other. Now, besides being just a really interesting concept that makes us question the nature of reality itself, we can actually use superposition to our advantage in quantum computers. So hopefully most of you are familiar with the fact that classical computers use bits to store information, and these bits can have values of either 0 or 1. And when we combine these bits, this allows us to perform complex tasks with classical computers. So in contrast, quantum bits use the principle of superposition. And so, you can think of the states 1 and 0 as being the up and down states I described on the previous slide. And so I'll just hopefully, I don't know if this animation is going to work, but instead of only being able to occupy, one state or the other, so instead of being able to go up or down, you can actually be, you can have any arbitrary superposition of these two states. And this essentially means that quantum bits can store more information than classical bits. And there are many different types of quantum bits, or qubits as we call them. And a lot of quantum materials research is focused on finding materials that can host states that we can use as qubits to engineer quantum computing platforms. And some of these qubits rely on superconductivity. And a lot of the materials that I and my colleagues study are superconductors. So I wanted to talk briefly about superconductivity because it is an excellent example of a quantum state that leads to behavior that we can observe on a macroscopic scale. So, for those of you who are unfamiliar with superconductors, superconductors are characterized by the fact that they can conduct electricity with absolutely no resistance at all. So no energy is lost to resistance. And this is really, an incredible concept if you think about how much energy we lose to resistance in all of our power transmission and electrical devices. Unfortunately, superconductivity normally only occurs at really low temperatures, so that prevents us from using this to our advantage in everyday technology, but there are still a lot of interesting uses for superconductors. And so in a superconductor, the electrons, the conduction electrons, form pairs called superpairs, or Cooper pairs, excuse me. And all of these Cooper pairs form a single quantum state. And I won't be able to give you a deep understanding of superconductivity, but I do want to give you a little illustration that might help you understand superconductors a little bit better. So imagine you have an arrangement of positively charged nuclei represented by these green squares, and then also negatively charged conduction electrons represented by these red dots. So as the electrons pass through the material, the positively charged nuclei will be, attracted to the negative charge on the electron, and this creates a region of positive charge here. And a second electron is attracted to this region of positive charge, and these electrons pair up, and they are basically propelled through the material by this attractive force with no resistance. Again, this is a highly simplified picture, but hopefully it gives you a little bit more intuition of how this pairing works in a conventional superconductor. And this picture doesn't always work, and I'll discuss that a little bit more in relation to my own research later on. So another cool aspect of superconductors is that superconductors expel magnetic fields. And this is called the Meissner effect. And this happens because there are currents on the surface of the superconductor, and these generate magnetic fields that will repel any external field. And this leads to magnetic levitation, where a superconductor will actually float over a magnet due to these repulsive forces. And superconducting magnets are actually can be used in levitating trains. I would highly recommend that you Google the Meissner effect if you have not already, because there's some pretty cool videos. So we use superconductors all the time in different technologies. We use them in MRI machines to generate strong magnetic fields. We use them also to measure very small magnetic fields. If we can figure out how to get room temperature superconductors, we could take advantage of this lossless power transmission. They're also used to detect single photons, and I worked on single photon detectors in one of my summer programs. These can be used in deep space communication. And also, as I mentioned, there are different types of qubits that rely on superconductivity. And this is kind of the broad motivation for my own work. So with that, I'll transition into a specific example from my own research working on the material strontium titanate. So strontium titanate is a crystalline solid, which basically means that the atoms are arranged in a particular way. So here we have the strontium atoms on the corner of this cube. We have a positively charged titanium atom in the middle, or ion rather, in the middle. And then we have oxygen ions that are negatively charged, forming an octahedron around this central titanium. And this is what's called a unit cell, which means this is the smallest repeated unit of this arrangement of atoms. And so basically, if you repeat this unit cell through all of space, this is what the material looks like on a larger scale, right? So we have this arrangement of atoms repeated over and over again in all three directions, and that forms our solid. So strontium titanate is an insulator, but if we add electrons to the system, it becomes a metal. And this metal becomes a superconductor at low temperatures. And furthermore, if we apply strain to the material, we can achieve a ferroelectric state where this titanium ion has shifted up and the oxygen anions have shifted down. And this results in a polarization, since the positive charges have shifted up, negative have shifted down. And so we get an electric field generated in the ferroelectric state. And so aside from the fact that strontium titanate can exist in all those states that I just described, we're mainly interested in this material because the superconducting state is really unusual. And one of the things that makes the superconducting state unusual is that the electrons move very slowly in this material. So the traditional picture of Cooper pairing that I described earlier doesn't really make sense. So to illustrate this, I'm going to go back to this highly simplified version for visual clarity. Keep in mind, of course, that what's happening in the real material is a lot more complicated than this. But we see that what happens when the electrons move very slowly is that we initially do get the nuclei that are attracted to this negatively charged electron. But by the time the second electron shows up on the scene, these nuclei have kind of moved back to their original positions. And therefore, these electrons can't pair because now there is, the lack of this attractive force, and then also there's this repulsion between electrons. So the traditional picture of Cooper pairing doesn't make sense. So there must be something else going on, and we want to figure out what it is. Another interesting thing is that ferroelectricity, so this polarization across the material, usually prevents the conduction electrons from flowing. So it usually destroys superconductivity. But in this material, in the ferroelectric state, the superconductivity is actually enhanced. And this is really highly unusual. And we want to understand why this is. And one of the reasons we care about this is that unconventional superconductors often have properties that can be useful for quantum computing. And the details of the reasons behind that are a little bit more complicated than what I want to get into, but that's kind of the motivation for studying this behavior. And so I personally want to understand the characteristics of the phase transition because we want to understand how this phase transition is related to the superconductivity. And when I say a phase transition, all I'm talking about is going from the state where the material is not ferroelectric to going to the state where it is ferroelectric. And there are two basic ways that this can happen. So here I've shown 4 repeated units of the material just to demonstrate this behavior. So in a displacive phase transition at high temperatures, all the titanium ions are centered in the unit cells. And then as we lower the temperature, they displace collectively. And we get our, our polarization, we achieve our ferroelectric state. But there's another way that this can happen. So sometimes at high temperatures, we have the ions displaced, but some are down and some are up, and the average polarization is 0. But then as we lower the temperature, all of these ions align, and we again achieve our ferroelectric state. And the type of transition that's happening in the material affects the properties of the material and could give us information about the relationship between ferroelectricity and superconductivity. And so I study this ferroelectric phase transition using computational tools. And so I just wanted to quickly close. I won't go into any detail about the types of tools that I use, but I just wanted to mention why computation is important. So computation is actually considered a third branch of materials research along with theory and experiment. And so why do we do computation? Why is this helpful to us? So first of all, it helps us understand and explain experimental results. So someone might observe a certain behavior of a material in an experiment, but they might not understand why that's happening. And computation can help give insight into why certain things are happening, which is extremely helpful. Computation also allows us to study systems under conditions that couldn't be achieved experimentally or would maybe be too expensive or just too difficult. We also have complete control over all the parameters when we are doing computation, which can be useful. And essentially, this allows us to make predictions and to determine future directions for experimental work, which is very exciting. So with that, I just want to thank my wonderful group, my advisor, John Harder, and all of our group members. And of course, I want to thank the Edelman Center for Quantum Innovation for funding my work, and CNSI for providing the computing platforms that I use to do my calculations, and of course, the Materials Student Association for hosting these talks. And I'd also like to thank everyone who mentored me and helped me as an undergraduate to help me get to this position where I am now. And I've put my email here, so please feel free to reach out to me with any additional questions. And I'll just show quickly the references for some of the images I used.
Well, thanks so much for your talk, Lily. The explanation you gave about quantum computing and materials is probably one of the clearest that I've heard, and I actually understand how it's so important now.
Great, I'm glad.
Yeah, so we're kind of running short on time, but I did want to ask you one question. You talked about how you did a lot of applied research in your undergrad, and now you're doing a lot of more like fundamental research. So what's I guess one advantage to fundamental research?
Yeah, so for me, it was definitely a big shift moving from more engineering and applied research to really fundamental research, where the applications are really far out. And I think my favorite thing about fundamental research is that you're really, as Vince mentioned, there's this kind of boundary of human knowledge. And when you're doing really fundamental research, you are really at the forefront of pushing that boundary, and you're really doing things that are fundamentally new, rather than kind of tweaking and improving science that's kind of already understood. So I think it's just really exciting because you're seeing fundamentally new phenomena, and you're just really pushing boundaries that could have a really big impact down the road, even if you can't necessarily predict exactly what application a certain material is going to be used for. So I personally think it's very exciting.
Yeah, definitely. So thanks everyone who tuned in today and who have been attending the seminars for the past few weeks. We had a really fun time putting this together and hope that it's been really helpful and informative for everyone. We will be posting the recordings of all of the talks to our YouTube page, which we will put in the chat right now. We will also be sending out an email with a follow-up survey to everyone who's been attending. And we would really appreciate it if you could fill it out so that we could improve this event for the future. So good luck to everyone who is still in school, and for everyone who is already out of school, have a great summer. Thanks so much for coming, everyone.
Thank you.